Welcome to the Schneider lecture on behalf of the Global Environmental Change section. I am honored to introduce today's speaker for the Schneider lecture. The Stephen Schneider lecture honors the life and the work of scientist and climatologist Stephen Schneider. Steve was an extremely influential scientist, and I'll say Steve because our speaker is also Steve. But I'm talking about Schneider. Steve Schneider was an extremely influential scientist with extensive national and international recognition for his research and policy analysis and outreach related to climate and climate change. The Schneider lecture is selected in recognition of outstanding scientific accomplishments in global environmental change and in communicating scientific results to the public. We are honored to have this year's Stephen Schneider lecture given by another Stephen Schwartz. Steve, this time I'm talking about Schwartz, is a senior scientist at Brookhaven National Laboratory, where his research centers on the influences of energy-related emissions on climate, with a focus on the role of atmospheric aerosols. Steve's research exerted a major influence on the drafting of acid deposition section of the 1990 Clean Air Act amendments. So we can thank Steve for some of the clean air we're enjoying today in the US. Steve is an author and co-author of over 150 papers published in peer-reviewed scientific journals. He was the editor of Trace Atmospheric Constituents, published by Wiley in 1983, and was co-editor of a 3-volume series, Precipitation, Scavenging, and Atmosphere Surface Exchange, published by Taylor and Francis in 1982. He's a co-author of Sea Salt Aerosol Production Mechanisms, Methods, and Measurements Models, a critical review published by the American Geophysical Union in 2004. He also served as the management team which developed and led the Department of Energy's atmospheric radiation measurement, the ARM program, which those of us doing aerosols are familiar as being a very important program, from the inception of that program in 1990 until 1999. Steve was educated at Harvard College, UC Berkeley, and did a Fulbright postdoctoral fellowship at Cambridge University in England. Steve lives with his wife, a retired teacher, in Center Mauritius, I hope I'm saying this correctly, in Center Mauritius on the south shore of Long Island, where he enjoys canoeing on the Forge River. They have 2 grown children, and this is important. Steve drives a hybrid gasoline-electric car. Please welcome Steve Schneider to give his lecture, Deep Insights from Simple Models. Please, Steve.
Thank you, Ali, for the kind introduction. Just for the record, I'm not Steve Schneider. I'm Steve Schwartz, but I'm delighted to be here for the Stephen Schneider lecture. I wish to thank the committee for the invitation to present this lecture. I want to thank Don Wubbles for nominating me for this lecture and for this honor, and it really is. I do wish to mention that I transitioned into climate science. We were doing acid deposition studies, but I met Steve Schneider early in that transition. He was very welcoming, and we all miss him. We miss him for his science. We miss him for his insights. Talk is entitled Deep Insights from Simple Models, and I hope to persuade you that we can gain deep insights from simple models. I thought I would wax a little philosophical at the beginning. What is a model? And what I tell students and young people, a model is a mathematical construct that tells us the consequences of what we know or assume. And then for a simple model, what makes a simple model useful? It has a small number of parameters. Those parameters are constrained by observations and or by theoretical understanding. It gives the right answer? No. It doesn't necessarily have to give the right answer. It could be right for the wrong reason, or it could be wrong and we could learn something from that. It should be transparent. For example, we should be able to see the fluxes that go through all processes. It should yield readily interpretable quantities, such as time constants. It should give the gist of the situation rather than an exact reproduction. It should allow readily for estimation of uncertainties and should allow for examinations of the consequences of changing the parameters, allow us to do what-if scenarios, examine even unrealistic situations. It should provide insight. It should illuminate more complex situations. So that's what I hope to do in this talk. I'll go through 3 examples. Aerosol radiative forcing, which I've spent a lot of time in my career on. This concept of transient climate sensitivity and what I call the cold turkey experiment. And then the 3rd example, the adjustment time of anthropogenic carbon dioxide. For the first example, aerosol radiative forcing, I want to back up to this paper, a very influential paper by Steve Schneider, 1971, with Rasul, that's Rasul, with a young Schneider and a young Jim Hansen in that photograph. An increase by only a factor of 4 in global aerosol background concentration may be sufficient to reduce the surface temperature by as much as 3.5 degrees Kelvin. They also said in that paper, it is found that even an increase by a factor of 8 in the amount of CO2, which is highly unlikely in the next several thousand years, will produce an increase in the surface temperature of less than 2 degrees Kelvin. Well, that latter statement was found to be a wrong, simple model very early, and that was corrected, and Steve came on board recognizing the importance of continued increases of CO2 on Earth's climate. But I want to stay with the aerosols. And this is a figure then from that paper. It looks dated. It is dated. It's 1971, not that long ago. It is showing the absorbed radiation by the planet as a function of aerosol optical depth on a scale from 0.01 up to 1 logarithmic scale, and showing the decrease in absorbed radiation. Why is that absorbed solar shortwave radiation decreasing? Because the aerosols are scattering light, and some of that light is going upward out of the climate system as a consequence of that light scattering, and that's the physics behind this particular figure. It's very interesting to replot this figure, which I've done in the way that we would do it now, where it's plotted as a forcing. So here's the forcing, a change in now watts per meter squared, versus optical depth on a linear scale, 0 to 1, with a slope of 86 watts per meter squared per OD. I should qualify this as cloud-free, as for a highly scattering aerosol. We'll come back to this figure later. But just to emphasize the importance of this, derate by a half for cloud fraction. We have an aerosol optical depth of 0.1. We're still talking something like 3 or 4 watts per square meter from such a scattering aerosol, should that figure be correct. So this is very important. An optical depth of 1 is not out, locally is not out of the question. We're finding that in many places in the world these days. And just again to calibrate you, a doubling of CO2, which we have not yet reached, is 4 watts per square meter in the other direction. Fast forward some 15 years. This is a photograph of Bob Charlson with myself hiding behind that beard. Kind of a story. I went to the AGU meeting in San Francisco in 1986. Some of you may recall that we had those meetings in a bunch of hotels out on Van Ness Street, and you had to take a bus to go from one place to another, and I did. I took the bus and I went to hear a union talk by this man, Charlson, who was talking about the role of marine phytoplankton that emit dimethyl sulfide that gets into the atmosphere and could exert a controlling influence on climate by forming sulfate aerosol that then would scatter light, the Schneider mechanism we just talked about. And I stood up in that lecture. I didn't know anything about climate, but I knew a lot about atmospheric sulfur chemistry. And I said, the experiment to test your hypothesis has been conducted. It's called anthropogenic sulfur emissions. Anthropogenic sulfur exceeded biogenic by an order of magnitude then and now. And what Charlson said in his response struck me as very important. He said, what you've said is very important. We need to talk. And which I thought was a great response, and we did. And out of that extended conversation came this publication, ultimately published in Science Magazine, 1992. Charlson, myself, and some experts in radiation transfer, some experts in atmospheric chemistry. Current climate forcing due to anthropogenic sulfate is estimated to be -1 to -2 watts per square meter, globally averaged, comparable to greenhouse, et cetera. This paper turned out to be enormously influential, and then we can look back and ask the question, why was this paper so influential? And I really think it was influential because of this simple model that's written as a one-line equation, a back-of-the-envelope calculation. The change in radiative flux at the top of the atmosphere due to the presence of an aerosol, and then there's a bunch of factors. Half the planet illuminated by the sun at a given time. The solar constant, transmittance above the aerosol layer, 1 minus fractional cloudiness, surface reflectivity, an upscatter fraction, the fraction of scattered light by the aerosol that goes into the upward hemisphere, mass scattering coefficient, relative humidity dependence thereof, then some chemistry, the source of SO2, the yield in the organic chemist sense of what fraction of emitted SO2 becomes sulfate, the lifetime, the residence time of atmospheric sulfate, all divided by the area of the Earth, which of all these quantities is the one we know the best. But it broke it down into some geophysics, some aerosol microphysics, some aerosol optics, some chemistry. And each of these factors here has received a lot of attention over the years to try to refine the initial estimate. We can also use that equation to do an estimate of uncertainty associated with that. Take the logarithm, get the uncertainty factor associated with each of these quantities. They multiply, square root of the sums of the squares of the log, and take the anti-log. But 50% here and 50% there, pretty soon it adds up to substantial uncertainty, a factor of 5 in that estimate. Fast forward another 23 years, a paper by Bjorn Stevens published in 2015. And he's citing that particular paper. He raised the specter of a relatively large negative radiative forcing. He goes on, I believe there is little foundation for the expectation that comprehensive modeling alone can provide a basis for reducing uncertainties and estimates of this forcing, or that somehow these models encapsulate uncertainty and understanding. And it goes on to say theoretical justification is given for the simple model used to interpret the forcing. So this is a table I prepared in response to Bjorn's paper, and over on the right-hand side for every one of these quantities is the factor of the number that we gave in that paper in 92 upon the number, his estimate that he's giving in his 2015 paper. And the color code is that red means that the Charlson paper was higher, and blue means the Charlson paper was lower. And the thrust of it when you get all done is that the Charlson estimate is about a factor of 2 higher than Bjorn Stevens' current estimate. And then we can look into reasons why. And I won't go into all of them. Oh, here's the Rasool number comparing this 86 to our 83 and to Bjorn's 29. The uncertainty in the radiative forcing side of this prompted us to initiate what may have been the first aerosol radiative forcing model intercomparison project that was led by Olivier Boucher and myself. And what we did was we carefully specified the aerosol. So we specified the composition, the relative humidity, the single scattering albedo, the surface reflectance, the wavelength at which we were measuring the shortwave optical depth. So all of that was carefully specified. Then we asked each group to do its radiation transfer calculation. And it's maybe good news and bad news. The number comes out somewhat lower than that 86 or 83, but it's very dependent on particle size, not surprisingly, and not shown a lot of other variables that we carefully specified. So it's a kind of a good news, bad news result that comes out of that. So let me conclude this example with the insights that we get. Expressing the forcing as a product of factors allows the examination of individual factors, quantification of the uncertainties, and points the way to improved quantification. Sulfate is still uncertain to probably a factor of 2. And sulfate is easy. Sulfate has chemistry that's relatively well understood, sources that are relatively well quantified. I compare that to the organic aerosols that weren't much on anybody's horizon at that time, with the possible exception of Novikov and Penner, and now are shown by mass spectrometry to be contributing as much to aerosol mass loadings as sulfate in many places of the world, if not globally. So, and it's much more complicated chemistry. It don't have the advantage of the conservation of matter. A very small fraction of a lot of organic gases makes its way to the aerosol phase. It's a much more difficult problem. So the sulfate one was easy. I want to turn to my second example, the transient climate sensitivity and what I'm calling the cold turkey experiment. And I have to explain cold turkey for those whose native language is not American English. If you have an addiction and you want to quit that habit abruptly, that's called quitting cold turkey. Well, what is our addiction? It's fossil fuel combustion. So that's the cold turkey experiment. Before I get to that, I want to talk about this concept, simple model, equilibrium climate sensitivity. The change in global mean temperature is proportional to the forcing. What change, what forcing? The long time change if in response to a sustained forcing. And that's the sense of this, and that's why it's called equilibrium. As a chemist, I have to take exception to the use of the word equilibrium. The system is not an equilibrium, it's a steady state at best. And equilibrium means equal and opposite fluxes on all paths, and we certainly don't have that in the climate system. We have short wave coming in and long wave going out. Still, it's called the equilibrium sensitivity, and is commonly expressed by multiplying by the forcing of a doubled CO2, and then given as the temperature that would result ultimately from an imposition of a doubled CO2 in the climate system at about 3 Kelvin. My assertion here is that this is a model that has outlived its usefulness. And I'm not the first to say that. I go back to another paper by Schneider. This is by Schneider and Thompson, 1981. What they show here is the response of a 2-box model, as well as a single box model, to a step function CO2 doubling at year 0. And it's on a log scale from 1 out to 1,000 years. And here's their single box with a mixed layer ocean, and it reaches its new equilibrium steady state at something like 50 years. But if they include the whole deep ocean, that doesn't reach its equilibrium steady state until something like 1,000 years. By adding another box, one for the mixed layer and a second box for the deep ocean, you get this plateauing here, which I'm going to denote as the equilibrium sensitivity, if we ratio it to the forcing. And so that's really not a new recognition with me. It goes back to this paper by Schneider and Thompson. What are the compartments? We have an upper compartment that consists of the atmosphere and the upper ocean, and we have a lower compartment consisting of the deep ocean. We have an equation with heat capacity and change in temperatures. That's an energy equation, a forcing or power equation, a forcing, a response term, and a coupling term. To look at it over here, we have a lot of shortwave energy coming into the planet. We have a lot of long-wave energy leaving the planet. We have a slight perturbation on the forcing and a slight perturbation on the energy leaving the planet, and a coupling to the deep ocean. So here are the references: Schneider 81, Gregory in 2000, independent My paper in 2008, independent, Isaac Held referenced Gregory, and Geoffroy really applied this to a whole bunch of GCMs, interpreting the GCMs in terms of their transient and equilibrium sensitivities. We get 4 model parameters out of that: a transient sensitivity, an equilibrium sensitivity, and 2 time constants for the upper and the lower compartments. This is an idealized simple model calculation. Constant forcing is a function of time on a 50-year time scale or a 1,000-year time scale. Vertical scales are different on the 2 sides. And then shown in the second row of panels here is the change in global temperature as a function of time. The thick blue curve is the upper compartment of the climate system. The red curve is what you would have if you reach the transient sensitivity, and the dashed curve is what you would have if you reach the equilibrium sensitivity. And then those 2 sensitivities are shown here on the ratio of the change in temperature to the forcing. And what you see is that on the 50-year time scale, we're pretty close to this transient sensitivity, way under the equilibrium sensitivity. And even out at 1,000 years for this ramped forcing, we're somewhat above the transient, but still nowhere close to the equilibrium sensitivity. Now we want to apply that to the real world. To apply that to the real world, we need forcing. And some of you may recognize this figure from AR5, it's figure 8.18, and it tries to summarize all of the forcings over the period of time from 1750 up to the present time, then 2011, and all the various forcings that I won't get into, other than to call attention to this bright green line, which is the sum of the 2 aerosol forcings as a function of time, evaluate the 2 aerosol classes of forcings being the direct light scattering and the influencing of cloud properties, adding those 2 together, and then using the estimated uncertainty on that year 2011 forcing, this is the IPCC's 5 to 95% confidence range, to then propagate back into time the estimated aerosol forcing over that period of time for what I will refer to in the rest of this portion of the talk as the best estimate aerosol forcing, the high magnitude aerosol forcing, and the low magnitude aerosol forcing is given by these uncertainty ranges. And of course, the total forcing is the uncertainty in the total forcing is dominated by the uncertainty in the aerosol forcing. So here's the total forcing as a function of time. We now have the forcings as a function of time for these 3 cases: aerosol, forcing, magnitude. I'm saying magnitude because it's a negative forcing of high, best, and low as a function of time. They're color-coded, and I'll stay with that color coding. Staying with the best estimate, we want to get the transient climate sensitivity. And the way to do that is just to lay the forcing curve on top of the measured temperature curve over the period of time, stretch the vertical scale or compress the vertical scale of the forcing to match the observed temperature change over that period of record, and then read off the transient sensitivity on the right-hand axis, on the left-hand axis for a forcing of 1 watt per square meter shown on the right-hand axis. So this one, for the best estimate, gives us a transient sensitivity in kelvins per watt per square meter squared of 0.35. And then we can do that with the other 2 forcing estimate curves and get from down to 0.27 as great as about a factor of 2 greater than that, 0.55 kelvins per watt per meter squared. So any of these forcings leads to, 1, a fairly good match with the observed temperature record between forcing and temperature, but 2, a transient sensitivity. We can use those numbers, put them into the transient, into the 2-compartment model that we just developed, turn the crank, and out comes the temperature record over the period of time. And the point that I wish to make here is that any one of these forcing sensitivity pairs does a pretty good job of matching the observed temperature record. This is what the philosophers of science call equifinality, reaching the same conclusion with different sets of inputs. And just to compare these to the measured temperature records that are shown in black for several temperature records, the CMIP models, the individual models in the spaghetti, and the CMIP mean. And the point I would make is that any one of these models does a reasonably credible job of reproducing the historical temperature record. Now the cold turkey experiment. What's the cold turkey experiment? Turn off all the sources of carbon dioxide and aerosol precursors from fossil fuel emission, and turn them off abruptly. And what's going to happen? Well, we need a forcing. We're turning off the aerosols. The aerosols go away in a week. What's the forcing? It's the negative of a negative forcing. The negative of a negative forcing is a positive forcing, and depending upon which aerosol forcing we were using, we could have that forcing as great as 1.88 watts per meter squared, as low as 0.09 watts per square meter, or the best estimate at 0.9. What about the carbon dioxide? Well, I thought that was going to be the easy part. And then I went to the literature to try to find out how quickly carbon dioxide disappears from the atmosphere if you turn off the sources of carbon dioxide. So this is a semi-log plot as a function of time out to 40 years. It is a plot of the fraction of excess CO2 above pre-industrial that would remain in the atmosphere after cessation of emissions from a whole bunch of different studies. What are they? They're model studies. It's an ensemble of opportunity. I had to go to the literature and get a whole bunch of studies of people who started at this or that initial concentration. I had to normalize these things up, digitize them, plot them up, and what we're seeing now with the straight lines on here are 1 over E lifetimes of 70 years, 100, 200, 500 years. Here's a model up here that the CO2 is staying constant, and here's infinity. So we've got at least an order of magnitude range on that CO2 adjustment time as seen in a bunch of these model calculations. Forcing, that's easy. Once I assume an adjustment time of excess CO2, 70, 200, 500 years, then I get the forcing in watts per square meter from the decrease of the SO2. So it's the forcing is going down. You're decreasing a negative forcing, a positive forcing, so the forcing is decreasing. That's easy. Add the aerosols to that. Now for every one of those 3 aerosol situations, I take the carbon dioxide, add the forcing for the carbon dioxide, so I get a nest of 3 curves for each aerosol forcing, and then I can display those and make my calculations for each of those forcings for the corresponding transient sensitivity. So let's look at the results of that. Here's first just the CO2. Turn off the CO2, and depending upon the climate sensitivity that goes with the different aerosol forcings, I get a nest of curves. They're color-coded as before. If the climate sensitivity is at a high end associated with the high magnitude aerosol forcing, we'll get an increase in global temperature from turning off the CO2 that might reach something like 0.1 or 0.2 watts per meter squared, and then decrease as the CO2 starts coming down. The faster that comes down, the faster the decrease. And if the transient if the aerosol forcing is lower, then we get the blue and the green curves, which are even lower increase of this unrealized temperature warming. Shown here over on the right-hand axis is the equilibrium infinite time temperature change that you would get if you maintained the CO2 constant, which is represented by these solid lines here. And you can see that there's a long way to wait before you get to that infinite time value. Now putting in the aerosols, if the aerosol forcing is low, it's pretty much like we had in the case before. Temperature goes up a little bit, and then depending on how quickly the CO2 disappears from the atmosphere, we get either leveling off or a slight decrease in the global temperature of about 0.1 Kelvin. Best estimate, something like 0.3 or 0.4 Kelvin, and then decreasing as the CO2 decreases as a function of time. If the aerosol forcing is at the high magnitude end of its range, then this temperature increase can go up to 1.3 Kelvin, turning off the negative of the negative aerosol forcing. So I thought this was kind of real important. just to summarize the insights from this, the transient sensitivity, I think, is a useful model. The aerosol forcing is uncertain, but coupled between with the climate sensitivities, the two-compartment model works fairly well. It can be used to examine the consequences of the abrupt cessation. We can look at the committed increase in temperature, and it ranges from minimal to 1.3. That's big, and thus has major implications. So I thought this was real important. I sent this to a high-profile journal, and it was not even sent out for review. It was, the article was stated as not being of broad interest to our readership. And it kind of defies my understanding why a paper like this should not be of broad interest to the readership. The only thing I can come back to is this a statement from the patron saint of uncertainty, Voltaire. Uncertainty is an uncomfortable position, but certainty is an absurd one. I think our community is very uncomfortable with the consequences of this uncertainty. Okay, I want to turn to my third example, which is the adjustment time of anthropogenic CO2. It was stimulated by this figure, which you've just seen. And my question is there any contribution that I can make to the understanding of CO2 that might help us refine the rate of decrease of excess CO2 if we were to do the abrupt cold turkey experiment on CO2 or otherwise understand the CO2 budget? So starting with the CO2 budget, this figure, or the template for this figure, may look familiar to a lot of you. This is from figure 7.3 of AR4. It's got a lot of numbers on it, and every one of these numbers represents a flux. Fluxes are in the italic. Stocks are in the upright type. The pre-industrial is in the black, the anthropogenic perturbation is in the red, the annual increments are in this bold blue. So, units, petagrams for stocks, petagrams per year for fluxes, and as I say, there are a lot of numbers on here. Some of these are known rather well, some are known not so well. In keeping with tradition, the fluxes are given to many more significant figures than the accuracy with which they are known in order to permit a subtraction. So here you have gross primary productivity canonically stated as 120 petagrams of carbon per year, respiration of 119.4. Well, we don't know either of those very well. Gross primary productivity is traditionally estimated as a factor of 2 greater than net primary productivity, which is taken as 60, but neither the 60 nor the factor of 2 is known very well. But this 0.6 turns out to be important in terms of a pre-industrial flux from the terrestrial biosphere into the ocean mixed layer. The 70 is important. Not all that important, but pretty important. I'm going to argue this is a geophysical quantity. It's the flux, it's the dry deposition flux of any not too soluble gas from the atmosphere to the ocean. What does that flux depend on locally and instantaneously? It depends on temperature, it depends on wind speed, wind stress, it's doing the mixing, and it depends a little bit from gas to gas on the diffusivity of the gas. But and then this upflux has to account for this extra 0.6, and so therefore this is in slight disequilibrium even in the pre-industrial state in order to make a net non-zero flux between the atmosphere and the ocean mixed layer. The other thing I really want to call attention to is the solubility of CO2 that can be inferred from the ratio of the stocks in the atmosphere and in the mixed layer. So in the pre-industrial, you've got 900 in the mixed layer, you've got 600 in the atmosphere, something like 3 to 2. For the anthropogenic increment, you've got 300 in the atmosphere, 30 in the mixed layer. It's 10 or 1, 9 to 1, the other direction. What's happening? The CO2 is getting less soluble. As you put more CO2 into the ocean, you're changing the acid-base equilibrium, so that becomes important. Sources, we have anthropogenic sources of fossil fuel emission at present time about 10, and we have land use clearing emissions, land use change emissions of about 1.4. What else is on here? Flux from the atmosphere to the terrestrial biosphere that's in response to the anthropogenic perturbation, fluxes to and from the mixed layer to the deep ocean and back. So those are all in some extensive quantities that we call them. The intensive quantities are the transfer coefficients, and this diagram becomes a lot simpler. We only really have 4 numbers that we have to concern ourselves with. A transfer velocity from the atmosphere to the mixed layer, that's this one. From the mixed layer back to the atmosphere, that's this one. If the fluxes were proportional to the stocks, this would be an equilibrium constant. It's not quite an equilibrium constant. It's a partial of the atmospheric stock to the mixed layer stock, but we know how to calculate that. Simple chemistry. The fluxes from the mixed layer to the deep ocean and back are given by a global piston velocity. And that global piston velocity is about 5 meters per year. Where does I get that number from? I went to the literature that I was familiar with, which is the uptake of heat by the deep ocean from the upper ocean, which people have been measuring by soundings and determining the temperature of the ocean. Knowing the heat capacity, you get the heat content of the ocean, take a derivative of that with time, and you get the rate of heat transfer into the deep ocean. And so that's where I got that number from. My analogy is you're pouring cream into your black coffee. You're diluting it in the color. You're adding the cream color to it. At the same time, you're diluting it in the temperature. It's getting cooler. Just exactly the same transport mechanism of heat or carbon dioxide dissolved in organic carbon or any other tracer. So that's where these two numbers come, a single piston velocity of 5 meters per year. And the only number we don't know in this whole calculus is the transfer coefficient from the atmosphere to the terrestrial biosphere. So we say, well, that's the difference of the total sources into the atmosphere less the decreases in these other stocks by the transport from here's the atmospheric growth, and then here's the change in the mixed layer stock and the change in the deep ocean stock. So you subtract those off and you get this final transfer coefficient by difference. That's sort of the one assumption that's going into this particular model. We need emissions. We need emissions as a function of time. There is a community that has been examining emissions from both fossil fuel combustion and from land use clearing emissions. These are conveniently tabulated annually by LeCaire and the reports from the Carbon Project. So we have those numbers. We're ready to go. We can push the execute button on our ODE solver. Here it is. The black line is what the model tells us. The blue circles and the red circles, southern hemisphere, and then total global of measured CO2. So I would say this model does a pretty good job. Does it do a perfect job? No. What does it miss? It misses what happened here in the 1940s, the so-called flattening of CO2, which is documented now in an increasing amount of work, and nobody knows what it's due to, but the thought is something changed in the ocean circulations. Other than that, I think this model does a pretty good job for 4 parameters, so therefore we can try to use it for understanding, but also for doing what-if experiments. Well, what's the what-if experiment? It's the cold turkey experiment. Turn off the sources of CO2 and what happens? And what happens is that the CO2 goes down. And how fast does it go down? Fit it to a single exponential out over 100 years. 60 years, 1/8 time for that exponential. We can go back and we can examine the near equilibrium between the atmosphere and the mixed layer ocean. So the equilibrium and the mixed concentration of dissolved inorganic carbon in the mixed layer ocean given by the green, the number that we get out of our model given by the red, these are in pretty close equilibrium. It's the leaky bucket, if you wish, so that the mixed layer ocean trails the equilibrium by a slight amount. Here's the departure on that. But it gives us more insight. What's the insight? If these two compartments are near equilibrium, think of them as a single compartment. Well, then that really simplifies the calculation of the lifetime, an analytical estimate of the lifetime as the sum of those two stocks upon the sum of the two fluxes out of those two compartments, the atmosphere to terrestrial and the net flux from the mixed layer into the deep ocean. So that's what's plotted here. Here's our 60 years at the time. It's kind of constant over this period of time. What happens later is as the deep ocean fills up and starts giving you a return flux back, you're dominated increasingly by the flux to the terrestrial biosphere, which we've assumed to be proportional to the excess CO2 in the atmosphere. We can check that, and that's what's shown here. So we look at what the measurements that we have, the atmospheric concentrations, take the derivative so that you get this, subtract from the source so that you get the sink rate out of that, and then we can compare that to what our model is telling us what that sink rate is over the period of time. So again, I think that very much supports the assumption that the flux to the terrestrial biosphere is proportional to the excess CO2 fertilization effect, if you wish. We can do what I call the worm turkey experiment. Suppose we said, well, we can't totally decarbonize our economy, but we can reduce emissions. How much can we need to reduce emissions to hold CO2 in the atmosphere constant? The amount we need to reduce CO2 emissions to hold the atmosphere constant is equal to the sum of the flux into the terrestrial biosphere and then into the deep ocean. Well, our model tells us that, so if we reduce our emissions by that, we can hold the atmospheric CO2 mixing ratio equal to a constant at its present value or whatever time we choose to do this. So here's where my result comes in on this previous chart. It is, again, in American slang, kind of way out in left field. It's a lot shorter than prior values, but that's where it stands. What are my insights? We can represent the historical budget very accurately with independently, with a 2 or 3 compartment model, with independent observationally based transfer coefficients, adjustment time of about 60 years. We can stabilize emissions by having current emissions, stabilize concentrations by having current emissions. The adjustment time is much shorter than most present estimates, and this would be good news for strategies to meet climate change targets. I've put that last sentence in subjunctive. I don't know if this is true. This is what the model is telling me, and when I was a PhD student, my PhD advisor, Harold Johnston, gave me a small model calculation, and he said, Steve, when you do a model calculation, don't format your output too nicely, because the nicer you format your output, the more likely you are to believe it. So we need to be skeptical of models in general, especially models of our own, especially if they're nicely formatted. So I put this in the subjunctive, but if in fact this is correct, and I think it is, it would be good news in terms of strategies to meet climate change targets. But on the other hand, by saying so, I'm introducing a little bit of moral hazard. Well, we don't have to worry about the CO2. We'll let our kids worry about the CO2, and in the meantime, we can continue to emit. So I'm very concerned about the interpretation that might come out of this conclusion. I want to turn back to Steve Schneider. Steve has kind of gotten a bum rap in some quarters by this quotation from a statement that he made to call attention to the concern over climate change, we have to offer up scary scenarios, make simplified dramatic statements, and make little mention of any doubts we might have. That's sometimes generally quoted out of context. The broader context, as scientists, we are ethically bound to the scientific method, which means we must include all the doubts, the caveats, the ifs, the ands, and the buts. And I certainly concur in that. Here's kind of my own view. Our highest obligation as scientists is to the truth as we understand it. We must report our findings, our understanding honestly, accurately, and fully, including the uncertainties and their implications. This extends to the societal implications. We should convey these implications without exaggeration. I think the actual state of the climate change is such that we do not have to do any exaggerating. We just simply have to point out what's been happening in front of our own eyes. And we should express our understanding in the simplest terms possible. So that really concludes my talk on, about the insights that I think we can get from simple models. I thank you for your attention.
Okay. Thank you, Steve. We have time for a few questions. If you will put up your hand, state your affiliation, and ask the question.
I noticed your cold turkey and asymptotes to something at or above pre-industrial. Is it possible that the hysteresis of the vegetable kingdom might actually cause it to asymptote even lower?
The question was about the asymptoting in the cold turkey experiment. Does it asymptote back to pre-industrial, or does it asymptote somewhere differently? And that's, of course, the answer to that's not known. In my model, it will asymptote over a longer period of time than shown in that graph to the pre-industrial. Even when the deep ocean fills up, you still have the terrestrial sink, which, according to my model, is taking up carbon dioxide from the atmosphere with a net flux that is proportional to the delta between pre-industrial and the present time. So it will asymptote down. Whether that, in fact, will be borne out by the terrestrial vegetation whom we would be relying upon is of course, not known.
The hysteresis was the key question.
Yeah, I don't know that there's hysteresis built into this model, but there is a long time tail on that one, because as you go out in time, the ocean is filling up and there's less and less net flux into the ocean, so the time constant is getting longer as it approaches the single time constant given by the flux to the terrestrial biosphere.
Questions? Yeah.
Nope. Oh, there we go. Catherine Duffy, Northern Arizona University. I have a question about the CO2 fertilization effect and simple models. Essentially, in the terrestrial biosphere community, especially in models, we keep on seeing this kind of up ramp of terrestrial carbon or the terrestrial biosphere productivity due to the CO2 fertilization effect. But speaking of simple models, I keep on coming back in my mind to the solubility of CO2 at temperature in water, especially in comparison to O2 in water. And so as a chemist, what is your perspective on the CO2 fertilization effect given that simple model?
Well, I think it's a two-part question. One has to do with the temperature sensitivity of CO2 solubility, and I think related to that is again, the question that the previous question spoke to is can we continue to rely upon the same transfer coefficient into the terrestrial biosphere? We know a lot about the solubility of CO2 in seawater, and we know the temperature dependence, and it's governed mainly by the temperature dependence of the Henry's law coefficient, and there is indeed some temperature dependence on that Henry's law coefficient, but for that to make a big difference is going to require a lot of temperature change. The temperature change of 1 or 2 kelvins is not going to change that CO2 solubility in seawater by very much. And as far as the terrestrial biosphere is concerned, that's a bigger unknown. We're putting all kinds of stresses on the terrestrial biosphere from temperature, water stress, insects, you name it. And whether we can continue to rely on the terrestrial biosphere to continue to take up the CO2 proportional to that excess with the same proportionality constant is really not known. Yeah, the question is ultimately how does the plant take up the CO2? It's done inside the substomatal cavity. intracellular fluids where it gets taken up, if those leaves are increasing, we know for a lot of reasons, plants are always under competition between how do I keep my water and at the same time get CO2? Well, I'll try to keep my stomates open as long as I've got enough turgor from the water to survive. But if the temperature gets high enough, if the relative humidity gets low enough, if I get dry enough, first thing I do is I close my stomates. So if we have increases in temperature and the plants are closing their stomates more, that could be a mechanistic reason why that proportionality constant might change in a future climate.
That's what I meant by hysteresis, by the way.
Yeah. Okay, I know we have a lot of experts on CO2 in the room. Okay.
Hi, Steve. Mike McCracken, Climate Institute. So my recollection of development of simple models, and this has been done, for decades or something, is that the problem with the climate model being a couple of box kind of thing is that it decays to something that isn't the actual climate of the Earth. That is, we have a cold ocean and a warm atmosphere, and what was done was basically to put a bypass from the upper ocean and create deep water going down to the bottom, cold deep water, and that pushes the heat up. So you have a downward and an upward motion, and then you will decay to the right situation instead of just sort of diffusing heat, essentially, as you're doing, or moving heat to an equilibrium into the ocean. And that seemed to work much better when you were trying to represent the actual climate of the Earth. I think that's the way the magic model works, for example, Wigley's magic model and other things. So I guess I'm curious why you went even more simple. And for the carbon cycle model, given how much carbon is in the ocean, that was actually an original criticism of Arrhenius when he did it, that could the CO2 concentration go up? There's so much more carbon in the ocean that the carbon will get taken up and you can't increase the atmospheric loading. And it took some understanding about the upper ocean and the deep ocean and some of the cycling to try and get a better representation of the cycle.
Well, a couple of issues here. One has to do with the CO2 and the solubility of CO2. And I tried to point out, as I'm sure Arrhenius recognized, that the solubility of the incremental CO2 is an order of magnitude less than the solubility taken as a whole of the pre-industrial CO2. So, but even under those circumstances, there is a sink from the mixed layer ocean to the deep ocean. Now, how you wish to represent that sink for either heat or carbon dioxide, there's a community that considers it more diffusive. There's a community that considers it more motion of parcels, and you count the volume of the parcels that are going from the mixed layer ocean to the deep ocean, and then that gives you a piston velocity. So I think a model that is a fairly accurate model at the present time. Whether it can be extended into the future is because of potential changes that would occur in ocean circulations or the like. It becomes more problematic. But I feel rather confident in its representation of these fluxes by whatever mechanism between the several compartments.
Steve, this is Ines Fong. Thank you for a very provocative talk, and I would like to paraphrase Charleston and say, let's talk. I think the insight I got from your turnover time, the ocean time, is that if we had a big stirrer of the deep ocean, and I think from the figure you've got 3,583 meters. If we stir the 3,500 meters of ocean rapidly, as you do here, that you have a constant concentration, then your milk is diluted uniformly through your coffee, then it is very easy for the anthropogenic CO2 to penetrate to the deep ocean. Whereas if you look at the F11, F12 observations now, the transects along the Atlantic and the transects along the Pacific, the penetration depth of F11, F12 is only somewhere between 500 and 1,000 meters. So it really is the effective mixing depth of the ocean is slowly increasing with time. And so it would be interesting for your model to build that in, okay, to see what kind of mixing, not this big stirrer that you've got in your model, what, in the range of that you show between, I forget what's 200 and infinity, a long time, whether that is related to how the deep ocean is stirred or not stirred, and how fast things can penetrate into the deep ocean.
Yeah, thank you, Inez, for that comment, and it does strike to the heart of my model, in the sense that the return time that is in my model is predicated on a stirring, if you wish, of the coffee in the deep ocean. There is a certain amount of bulk flow from the upper ocean to the deep ocean. There's a certain amount of bulk flow diffusion, molecular diffusion, eddy diffusion. Those are very slow processes. But so the mechanisms of this transport become important, and ultimately, over time, it may well be that time constant for the return from the deep ocean will increase. I would add to that, however, that even in the model that I was showing here, as the deep ocean was filling up with its time constant of 600 years, and giving less and less of a return flux, still in this model, the terrestrial biosphere was continuing to do its thing, and so the time constant went up from something like 60 years up to something like 80 years over that period of time, as a consequence of diminishing the ocean sink. So I think these are very real issues, and I think the studies such as you mentioned of geosecs and penetration of CFCs are very pertinent to this. I note that the modeling community, such as Malakoff Fletcher, are using those data to try to infer the uptake rates in their models, and getting kind of comparable numbers of 2 petagrams per year net into the deep ocean. So I'm not saying this is the last word, but I think it's a very insightful word.
So,
the deep ocean wouldn't radiate to space.
I'm,
the deep ocean, it would be so cold that it would cease to radiate heat to space.
okay. Thank you for that further comment.
we can continue the last discussion. One more question. Last one.
Hi, Steve. Rajan Chakraborty of Washington University in St. Louis. I had one quick question, which is a little bit off tangent, and I just, you have been an aerosol player since the 70s. I wanted to get your scientific opinion, or your personal opinion in this case, on the whole stratospheric geoengineering concept using aerosols, which have been floating around. Given your insights using all these simplistic models, investigating every segment, what do you have a perspective on it?
I didn't get the whole question from that. My perspective on?
Stratospheric.
Stratospheric geoengineering.
On the geoengineering question. Yeah, you're in an engineering department, so you probably know better than anybody else that you don't try to engineer some kind of a project until you understand it. And I say our understanding of the stratosphere and of the climate system is still at a stage where it would be foolhardy on our part to try to inject material into the stratosphere in the hope of offsetting by light scattering the warming from increasing CO2. Foolhardy.
So let's thank Steve again.
We can do photos later.
And I have a little award for you.
Thank you. Thank you very much.
We'll do the photo later.
Okay.